Give me a minute. I'll tell you what I'm doing after I'm done. Okay, what was I doing? I have to, this thing cuts off after an hour if we don't do something to extend the time. So I manually extended the time 3 times by 5 minutes so that we'll have plenty of time to do our 75-minute lecture. So anyway, any questions about anything? Do you remember what we were talking about last time? Yes. Frequency response. Frequency response, specifically, so we started talking about frequency response of, and we're focusing here for now on causal FIR systems. Okay, now essentially there's a couple of ways of calculating the frequency response. So if the system is governed by, so say the system obeys this difference equation, y of n is equal to the sum from k equals 0 to, say, cap m of bk, x of n minus k, then the frequency response, and by the way, because the bk's are the same as the values of the impulse response at time k, it's the same thing as h of k, x of n minus k, for the k term in the sum. Then the frequency response function is this, h hat of omega hat, and again, this is my notation, it differs from that in the book, equals the sum from k equals 0 to cap m of bk e to the minus jk omega hat, and that's the same as the sum from k equals 0 to m of h of k e to the minus jk omega hat. Okay, now we noted last time, among other things, that first off, h hat of omega hat determines the system completely. From h hat of omega hat, you can figure out h of k for all k, or the bk's. So you can figure out the entire I/O behavior of the system just by looking at h hat of omega hat. So h hat of omega hat determines, and of course, is determined by the system. Okay, that's one thing. Another thing is h hat of omega hat is conjugate symmetric. In omega hat, all that means is that h hat of minus omega hat is the complex conjugate of h hat of omega hat. And also, h hat of omega hat is 2 pi periodic in omega hat. And this 2 pi periodicity condition leads to the custom that people have of graphing h hat of omega hat only on the interval minus pi less than or equal to omega hat less than or equal to pi. So we represent h hat of omega hat customarily in terms of magnitude and phase plots on the interval minus pi less than or equal omega hat less than or equal pi. And at the very end of class last time, we started doing a few examples of these. Okay, some pretty simple examples like the zero system, the identity system, the pure N1 shift system. And when the pure N1 shift system, when N1 gets big, doing the phase gets a little complicated. You have all these little piecewise linear branches, but whatever. We did a couple of those. And those are examples, standard examples from the book. And now I want to do a couple more. So we started a few crucial examples. And I can't emphasize enough. So these are examples that it's important to understand these. So understand them and how we get them and all that. All right, so here's a few more. All right, there's one that the book calls a high-pass filter. Okay, so the book calls this one, and I'll put this phrase in quotes because really, you know, we haven't talked about, like, it kind of makes sense when you're thinking about continuous time signal processing, what high pass and low pass means, but what does it mean in discrete time? We haven't really dealt with that yet. I'm going to save that up for a little while. So this is a high pass filter, and I promise you that later we'll see why we call these things, why we name it this. Okay, and it's about the most rudimentary high-pass filter you can build, and it has the I/O relationship, so the system obeys this difference equation. Y of n is equal to just the difference between x of n and x of n minus 1. Okay. What is the frequency response of that system? Here, it's convenient to use the other way of figuring out frequency response. We could do it this way. We could just do this. The h of 0 is 1. The h of 1 is minus 1. We can figure out the frequency. Well, let's do it that way first, and then we'll figure it out the other way as well. Okay, so what is h hat of omega hat? Because in this equation, b0 is equal to 1, b1 equals minus 1, thus h hat of omega hat is equal to 1 minus e to the minus j omega hat. Another way of figuring this out is to use the picture that I drew last time, and this is a picture that comes in really handy when you're dealing with a system where someone doesn't tell you what the BKs are right away. They just tell you sort of the box that relates the input and the output. So here's the picture. E to the j n omega hat goes into the system. What comes out is h hat of omega hat, e to the j n omega hat. So let's use this picture, and we'll get the same answer for h hat of omega hat as we did before. Put e to the j n omega hat for x of n, and you get y of n. So you set x of n equal to e to the j n omega hat. You get y of n equals x of n, which is e to the j n omega hat, minus x of n minus 1, which is e to the j n minus 1 omega hat. You factor e to the j n omega hat out of both terms on the right-hand side, and you get 1 minus e to the minus j omega hat times e to the j n omega hat. Thus, the thing in parentheses has to be h hat of omega hat. Okay, so that's the frequency response figured out two ways. Now we want to graph the magnitude and the phase of that thing. How do we do that? Well, we're going to use a trick, and this is a really useful kind of manipulation. And this example, the next example, and the final example we're going to do here today, all illustrate using this trick to figure out the magnitude and the phase. Instead of like writing h hat of omega hat in terms of real and imaginary parts, we're going to play around with it a little bit. So to get magnitude and phase, let's manipulate. Okay, so what is h hat omega hat? H hat omega hat is 1 minus e to the minus j omega hat. We factor out of both terms here e to the minus j omega hat over 2. And what that does is it symmetrizes what's in the parentheses, comes out to be this, e to the positive j omega hat over 2 minus e to the minus j omega hat over 2. And you may say, well, why did we do that? Well, what's inside the parentheses? What is that quantity? Anybody care to hazard a guess? Critique? Yes. Well, actually, you're missing a 2. It's 2j sine of omega hat over 2. So this is 2j sine of omega hat over 2, e to the minus j omega hat over 2. By Euler. Okay? It's one of Euler's formulas. If you take e to the j theta minus e to the minus j theta, you get 2j sine of theta for any real theta. All right, so let's play around with that a little more. What is j? J is e to the j pi over 2. So this becomes, I can absorb this into the second term. I get 2 sine omega hat over 2 times e to the minus j omega hat over 2 minus pi over 2. Boom, just like that. And this helps us graph the magnitude and phase of h hat of omega hat. How? What's the magnitude going to be? H hat of omega hat magnitude equals, anybody want to give that one a try? Okay, who am I going to pretend is going to answer this question? Stefan. Well, almost, okay, almost. He says it's 2 sine omega hat over 2. What's wrong with that? What's missing? What's missing there? H hat of omega hat has to be a non-negative number, right? And if I let omega hat go a little bit less than 0, this becomes negative. See? So we need absolute value of that thing. Okay? So what does it look like? Graph versus omega on the interval, omega hat I should say, on the interval minus pi to pi. It looks like this. So it's going to go like this, and it's going to go like this. Looks just like a sine wave going up. And what is the value at the peak? The right hand? Yes. It's 2. Very good. All right? So that's the magnitude. What about the phase? Here's our formula for, and by the way, I used here the fact that the magnitude of this part of h hat of omega hat is 1, because whenever you have e to the j theta, that has magnitude 1. So what is the phase? The phase is just the thing that multiplies j in the exponent. Kind of. We have to be careful. We might have to make an adjustment to get the phase between minus pi and pi. So let's see how this works. So as for the phase, nominally, let's call it the original phase. The original phase is going to be whatever multiplies j in the exponent. Kind of. Because 2 sine of omega hat over 2 can be negative. That adds a pi to the phase plus whatever. So we might say we need to take into account the sine of 2 sine omega hat over 2. It's positive when omega hat is bigger than 0 and less than pi, but it's negative when minus pi is less than or equal to omega hat is less than 0. So what does that do? That adds a pi to the nominal phase. The quote-unquote nominal phase. And what do I mean by the nominal phase or the original phase, whatever? Depending on my mood, I use different words for this. And by the way, this room is running low on chalk, so what's going to happen is if I come in here, I'm going to have to bring my own box of chalk, which fortunately I have in my office. Okay, so nominal phase is whatever multiplies j in the exponent. Namely, minus omega hat over 2 plus pi over 2. That's what multiplies j in the exponent. So this is what j multiplies in the exponent above. So we start our graph of the phase of h hat of omega hat by first graphing that nominal phase and then adding a pi to it, and maybe even doing more manipulations to get it between minus pi over 2 and pi over 2. So let's see what happens when we do that. So this is the nominal phase, minus omega hat over 2 plus pi over 2 versus omega hat on the interval minus pi to pi. Okay, what is it going to be? There's pi, there's minus pi. What is it at omega hat equals 0? It's pi over 2. What is it at omega hat equals pi? It's 0, and it's linear, so it looks like this. And what is it when it goes negative out here? Because this goes all the way up to pi, right? So this is pi here. Let me erase that to make it more legible. So this is pi, and this is graphing minus omega hat over 2 plus pi over 2 versus omega hat. Now what we have to do is, when omega hat is less than 0, we have to shift that down by pi, the left-hand side. We have to, we don't want to shift it up because it takes it out of the minus pi to pi interval, so we shift it down by pi. So you shift the left side down by pi to account for the sine of 2 sine omega hat over 2 when omega hat is less than 0. Thus, the phase, drum roll please, isn't it cool that it landed right under the magnitude plot? Maybe we should teach 2200 in this room from now on. So this is our final graph for the phase of h hat of omega hat versus omega hat. It goes pi over 2 out to pi. So this is pi over 2, and when I shift that left side down by pi over pi, I get that same thing, sort of symmetric there, like so. So this is minus pi over 2, and this is minus pi. So that's the phase. Okay, any questions about this? Remember I said it's crucial that we get these examples, get a good command of these examples, because these are really, really important examples. Any questions about that derivation? Okay, that's a good question. Let me go over it one more time. Okay? This h hat of omega hat takes a special form. And all the examples today, by the way, are going to take the same special form, and we'll have a lot more to say about that later. It takes the form real valued function of omega hat times e to the j something. And the something is linear or affine or whatever in omega hat. The real valued function multiplying that can be positive or negative depending on the value of omega hat. 2 sine omega hat over 2 is negative when omega hat is less than 0. So the phase of that whole number, h hat of omega hat, is going to be whatever multiplies the j plus or minus or whatever pi when this thing is negative, when the real value thing is negative. And we have to go carefully to the real value thing multiplying the e to the j thing and figure out the sign of it on various segments. We'll see that in the third example. That's going to get pretty messy. Well, it's not that messy. I guess it depends on your definition of the word messy. But anyway, that's a good question. All right. So now we did a low pass filter. Let's do what the book calls a high pass filter. Sorry, we did a high. This is a high pass filter. Now let's do what the book calls a low pass filter. So next example, the book calls a low pass filter. All right. So this is not the only. By the way, this first example isn't the only high pass filter in the world. This is not the only low pass filter in the world, but it turns out this one works. So y of n is equal to x of n plus 2x of n minus 1 plus x of n minus 2. Okay, and I just want to make sure I got that one right. I don't want to go through the whole example and have it end up really messy. Yep, okay. So that's the governing difference equation. How do we figure out the frequency response? We could do it with the BK method. We could say B0 is 1, B1 is 2, B2 is 2, or B2 is 1, and plug into the formula. Let's instead use the picture. E to the j and omega goes in, h hat of omega hat, e to the j and omega hat comes out. So to get h hat of omega hat, use the picture. Maybe we should call it that. Use the picture method whenever I say find the frequency response using the picture method. It would be cheating, lecture cheating, if I just left that picture up without rewriting it. So I'll do that. I'm entitled to cheat when you're not in the room, okay? This is the picture we want to use. If you put the signal e to the j and omega hat into the system, what comes out is going to be frequency response times e to the j and omega hat. Set x of n equal e to the j and omega hat. Then, what is y of n? Y of n, x of n, so e to the j and omega hat, plus 2x of n minus 1, plus x of n minus 2. Notice to get x of n minus 1 and x of n minus 2, all I do is everywhere I see an n and x, I plug in an n minus 1, plug in an n minus 2. Now what? Now we factor e to the j and omega hat out of the right-hand side. And what's left over? The thing that multiplies that has got to be the frequency response. So we get 1 plus 2 e to the minus j omega hat plus e to the minus j 2 omega hat, all that times e to the j and omega hat. And that means the frequency response is the thing in parentheses. Okay. So far, so good. Just want to make sure. Because now we're going to graph the magnitude and phase, and we're going to use a manipulation along the lines of the one we used for the first example. So again, to get the magnitude and phase, we manipulate. All right. So h hat omega hat is 1 plus 2 e to the minus j omega hat plus e to the minus j2 omega hat. What do? We factor something appropriate out of this right-hand side to make something nice and symmetric multiplying it. So what is that going to be? By the way, you learn how to do this over time. This is not, I'm not expecting you to have been able to say, oh, what a cool way, here's a cool way to figure out magnitude and phase. Let's play around with this and make it a real valued function times e to the j something. No, that's not something you're supposed to come up with on your own. Maybe some of you really clever people, like Alex Na over there, could come up with this on their own. But for now, I'm just saying this is something that you learn by practice. I factor e to the minus j omega hat out of every term, and I get e to the j omega hat plus 2 plus e to the minus j omega hat left over. Okay? Now, what's inside the parentheses? Somebody else, because Critique guessed it earlier. So someone else has to answer this one. Nick. Yes, exactly. By Euler, the sum of the first and the last terms here is 2 cosine omega hat. So this is the same as 2 plus 2 cosine omega hat comes out to be 2, 1 plus cos omega hat e to the minus j omega hat. By Euler. Okay? Now again, this is of that form, real valued function of omega hat times e to the minus j something, or e to the j something. In this case, the real valued function is always non-negative. So the nominal phase is going to be the actual phase. So let's go through that and see what happens. What is the magnitude? H hat of omega hat is the absolute value of 2, 1 plus cosine omega hat. And because cosine of omega hat is always bigger than or equal to minus 1, we don't even need these absolute value signs. What does this look like versus omega hat on the sacred interval minus pi to pi? Okay, so here's pi, here's minus pi. Oh, that's terrible. Let's move this pi out. Still bad, but not as bad. All right, so what is this? What does it look like? What I like to do is look at some key values of pi. So what about at omega hat equal, or key values of omega hat? What about at omega hat equals pi minus pi? What is the cosine then? The cosine of pi is minus 1. The cosine of minus pi is minus 1. Added to 1 gives me 0, so it's 0 out here and here. And what is it in the middle? Cosine of 0 is 1, so it's 2 times 2, and that's 4. So it takes on the value 4 at omega hat equals 0, and it takes on the value 0 at plus and minus pi, and you could see for yourself that it turns out to be this. Okay. All right, let me make sure I buy that. Yeah, if you take a cosine curve and you shift it up by 1, and then you multiply that by 2, that's what you get. Like this is This is actually, to make it look better, the slope is going to come in and be 0 at pi minus pi. So let's make sure. There. That's what it looks like. So that's the magnitude. What about the phase? The phase is equal to the nominal phase because the real value thing multiplying the e to the j theta part of it is always non-negative. So here's the phase of h hat of omega hat versus omega hat. On minus pi to pi, it's just equal to minus omega hat. And I want to note that this is the same as the quote-unquote nominal phase because that 2, 1 plus cosine omega hat is bigger than or equal to 0 for all omega hat. Okay? So that's the magnitude and phase plot for this so-called low-pass filter. Everybody get that? Okay. So now, this is the last example I want to look at from the book. And part of the reason for looking at this example is because it leads to a function of omega hat that's going to play an important role as we go along. Okay, so the last example for now is what the book calls an L-fold running summer. Running. And sometimes the book calls it an L-fold running sum, and sometimes it calls it an L-fold running summer, so I'll put the mer part in parentheses here. And what is that? That's this. It obeys this difference equation, y of n equals the sum from k equals 0 to cap L minus 1, x of n minus k. So think sliding window. Again, to compute the value of y of n, you look at a window of length L of x values leading up to n. You sum all those up, you get the value of y of n. Slide the window one ahead, you get the value of y of n plus 1. Again, y of n plus 2, and so on. So, L-fold running summer. Let's figure out the frequency response of that. And again, let's use the picture. So using the picture, quote unquote, to get h hat of omega hat yields the following. Okay, so e to the j and omega hat goes in, h hat of omega hat, e to the j and omega hat comes out, so we get y of n equals sum from k equals 0 to L minus 1, e to the j n minus k omega hat. So this is true when x of n is equal to e to the j n omega hat. We can factor e to the j n omega hat out of every term in that sum, and we get this. Sum from k equals 0 to L minus 1, e to the minus jk omega hat. All that times e to the j n omega hat. Thus, by the picture, what's in the parentheses has got to be h hat of omega hat. So h hat of omega hat equals this. Sum from k equals 0 to L minus 1 e to the minus j k omega hat. Okay. Now we want to graph the magnitude and phase of that, as always. That's what is done with frequency responses. Okay, by cognoscenti, among whose number you count yourselves now. Well, maybe you're like proto-cognoscenti. What is the singular of cognoscenti? It's cognoscento, if you know Italian. But anyway, okay, forget about that. How do we figure out the magnitude and phase of this? We're going to manipulate it. Okay, and how do we manipulate it? Well, we're going to use we're going to use an incredibly important and useful identity that everybody should know. And this is the kind of thing to carry around with you. Like, write it on a business card size thing and stick it in your wallet, you know, so you can like look at it when you're like in a boring plane ride or sheltering in place somewhere, you know, whatever. And it's this thing I like to call the partial geometric series. Okay, so, to analyze this, we use this really important result called the partial geometric series. And this comes up, by the way, later on when we talk about Z-transforms, comes up all the time when you're dealing with signals and systems, especially discrete time, but not just discrete time. So we use this extremely useful result called the partial geometric series. And you've all seen this in some guise or another in your lives. And it goes like this. If I take the sum from k equals 0 to L minus 1, I'll write it in this form just so you know it looks like what we're dealing with over there. And I have gamma to the k, and gamma here can be any complex number. It could be any real number, any complex number, whatever. What is that equal to? That's equal to something when gamma equals 1 and something else when gamma is not equal to 1. All right, so I want you guys to help me out at least with one of these. What is it equal to when gamma equals 1? This is easy. Well, no. I don't want to say it's easy because then if you don't see it, you'll feel like hurt and I'm insulting your intelligence. So maybe it's not easy, but it's not hard. All right. So what is that equal to when gamma equals 1? Anybody care to hazard a guess? Okay, Danyu says L, and that is correct. Why? Because when gamma equals 1, the sum from k equals 0 to L minus 1 of gamma to the k is just 1 plus 1 plus 1 plus 1 plus 1, L times. Simple as that. Now when gamma is not equal to 1, it's a little more complicated. It turns out to be 1 minus gamma to the L divided by 1 minus gamma. Okay, now why is that true? Here, simple proof. So it's easy to show simple proof of the gamma not equal to 1 case. If I take 1 minus gamma times 1 plus gamma squared plus da 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 plus gamma to the L minus 1, what happens when I do that? And this will happen even if you do that. Okay, it's not just if I do it. What happens if we do that? 1 minus gamma. Well, I get all these guys from the 1. Minus gamma times all these guys from the minus gamma. So I get gamma plus gamma squared plus gamma to the L. And look what happens when I take that difference. One by one, the terms cancel except this and this. So all terms cancel but these. And so we get 1 minus gamma to the L. So the conclusion is that 1 minus gamma times this sum equals 1 minus gamma to the L. And if I divide both sides by 1 minus gamma, I get this identity. Okay? All right. So there. That's partial geometric series. Super useful. You want to know that. Or at least I want you to know that. Okay? So, you know, I would prefer that you want to know it. All right, so how do we apply that here? How do we apply this to our H hat and omega hat? So back to the problem at hand. H hat and omega hat is equal to the sum from k equals 0 to L minus 1, e to the minus jk omega hat. And that's the same as the sum from k equals 0 to L minus 1 of e to the minus j omega hat to the k, right? So if you take your contacts out or whatever, take your glasses off, this looks just like sum from k equals 0 to L minus 1 of gamma to the k with gamma equal to minus j omega hat. So this is what you're supposed to be thinking. You're supposed to be thinking, ooh, partial geometric with gamma equal to e to the minus j omega hat. All right? So what does it come out to be? It comes out to be 1 minus gamma to the L. So that's 1 minus e to the minus j L omega hat upstairs divided by 1 minus gamma. And I'm forgetting about the gamma equals 1 case for now. Just bear with me on that. 1 minus e to the minus j omega hat. Okay? So that's h hat of omega hat. And now we manipulate that similarly to how we played with the other ones. We kind of turn it into the ratio of two things that look a little more symmetric. And my conscience demands that I say, for now, for the moment, don't worry about the e to the minus j omega hat equals 1 case. We'll see what happens there. That's the same as omega hat is equal to 0 when omega hat is in the interval minus pi less than equal to pi. We'll deal with that. I promise. Okay? Why do you always look like you're doubting me? I bet you wonder who I'm talking to. I'm actually talking to someone. I'm thinking of your face. And you usually sit over there. But it's not an unfriendly kind of doubting. It's a kind of like, this is kind of cool, but I'm really not sure I buy it. Don't you have those moments in every class? I certainly did when I was in school. Anyway. All right, so let's manipulate this. So, and again, this is one of those things that you learn over time. It's not something you're expected to see right off the bat. What we're going to do is we're going to take h hat of omega hat, which is 1 minus e to the minus j L omega hat over 1 minus e to the minus j omega hat, and we're going to symmetrize the numerator and denominator similarly to how we symmetrize things when we're dealing with the low and the high pass filters. So what we're going to do is we're going to factor an e to the minus j L over 2 omega hat out of the numerator to give us e to the j L over 2 omega hat minus e to the minus j L over 2 omega hat times e to the minus j L over 2 omega hat. And we're going to factor an e to the minus j omega hat over 2 from the denominator, which gives us e to the j omega hat over 2 minus e to the minus j omega hat over 2. Okay, so that's first step. And now we Euler things. Numerator becomes two j sine of, and I'll write it this way, L omega hat over 2. Denominator becomes 2j sine of just plain omega hat over 2, and then those e to the minus j things collapse into e to the minus j L omega hat over 2, L minus 1 over 2 times omega hat. Okay? Just collapse those two exponents together and I capture them in a standard kind of form. The two j's cancel. Bottom line, h hat of omega hat equals sine of L omega hat over 2 divided by sine omega hat over 2 times e to the minus j L minus 1 over 2 omega hat. So again, we have this situation where you have h hat of omega hat is some real value function of omega hat times e to the j something. We've had this in all of our examples so far, and I'll touch back on that in a minute. Promised you a couple of minutes ago that we would worry about the omega hat equals 1 case in a moment, and now's the time to do that, or the omega hat equals 0 case. What happens when omega hat equals 0 here? What happens? Well, this part becomes a 1. What about this part? This part is kind of like sine theta over theta, except not, because it's sine L theta over theta as theta goes to 0. So we're going to have to mess around with that, but it's promising because you in the back of your mind you're thinking L'Hopital, is going to work this out, and it will. Now there's a name, there's a terminology the book uses for the ratio of signs there. So here's some terminology. And this is the book's, this thing here, sine L omega hat over 2 divided by sine omega hat over 2. They call this d sub L of omega hat. And that's called what the book calls a Dirichlet form. Okay? Now we've heard the word Dirichlet before. You might remember. When was that? Does anyone remember when we heard the word Dirichlet? I figured. I'll give you a second. We've actually used that word. It's a person's name, obviously, but. All right, when we talk about Fourier series and how and when they converge, yes, you got it. That we call those conditions the Dirichlet conditions, like the thing is continuous except for jumps, there's only finitely many jumps in any interval, and between the jumps is piecewise differentiable. Those are what are called the Dirichlet conditions. Well, that's one thing named after Dirichlet. This is another. Okay? And why does the book call it a Dirichlet form? Well, because officially, the Dirichlet function is something else. So they don't want to co-opt this phrase. So officially, quote unquote, Dirichlet function means something else in mathematics. So they don't want to use Dirichlet function to describe that, so they call it a Dirichlet form. And I'm just going to call it a Dirichlet thing because, you know, form just sounds too formal, okay, to me. So that's a Dirichlet thing. Caution, okay, in MATLAB. So MATLAB has a built-in thing they call Dirichlet function. And when I say function here, I'm just talking about a MATLAB function. And that turns out to be 1 over L times DL hat of omega hat, DL over omega hat. So if you find, if you're doing like a lab problem or something and, oh wait, why is this off by L? Or 1 over L, then it might be because you're using Dirichlet thinking it's that, which is 1 over L times what we call DL omega hat. So 1 over L sine L omega hat over 2 divided by sine omega hat over 2. So this is the difference. Caution. All right. Let's graph the Dirichlet function of omega hat versus omega hat on the interval minus pi to pi. And for doing it for general L gets hairy, so what I'm going to do is I'm going to look at L equals 5 because that's plenty complicated to illustrate all the important ideas. So let's graph dl of omega hat on the interval minus pi less than or equal to omega hat less than or equal to pi when L equals 5. And that will reveals the sort of the structure of the graph for general L. And just in case you've forgotten where we started all this, we're looking at the frequency response of the L-fold running summer. Okay, that's what we're looking at. All right, so what is dl of omega hat on minus pi? So let's see what it is. So this is going to be d5 of omega hat. All right. So here's pi. Here's minus pi. Is that good or bad? That's all right. Okay, so what do you do whenever you see, this is what I do at least, whenever I see a ratio like this, or anything with like sines and cosines in it, first off, I want to figure out like, where is it equal to 0? Like, what are the 0 crossings of this function? So let's do a little side calculation. Notice that the denominator is always positive, except that omega hat equals 0. So we don't have to worry about that. So what are the 0 crossings? Let's do omega hat equals 0 first. Let's use L'Hopital. So when omega hat is equal to 0, we use L'Hopital. And by the way, L'Hopital, you want to make sure when you write L'Hopital that you put the circumflex over the O, okay? Because otherwise it doesn't spell L'Hopital, it spells something else. And if you're interested, I know, you're probably not, but I think you know, it is, to me it's interesting. Whenever you see a circumflex over a vowel in French, it means that in some earlier version of the language, there was an S after the vowel, right? So see, hospital, right? L'Hopital. There's other like examples you can think of, like chateau has a circumflex over the A. That's like castle, okay? And wine, there's a wine called Côte du Rhône, C-O, coast. That's the coast of the Rhone River. You know. Anyway, L'Hopital. Put a circumflex over the O to find that dl of 0 equals what? What do you think it equals? If you take the derivative of sine L omega hat over 2, the derivative of sine omega hat over 2, take that ratio, evaluate at omega hat equals 0, you get L. All right, so L is the value at omega hat equals 0. What are the zero crossings? So when is dl of omega hat equal to 0? When is that true? I think someone texted me just now. No, someone sent me a link. I'll have to look at it later. Numerator, L omega hat over 2 inside of a sine function. It's when L omega hat over 2 is equal to an integer multiple of pi. Oh, and because we're doing this for L equals 5, this comes out to be a 5. Sorry. So when is 5 omega hat over 2 equal to pi, for example? That's when omega hat is equal to 2 pi over 5. When is 5 omega hat over 2 equal to 2 pi? That means omega hat is 4 pi over 5. And the same is true for negative pi and pi. So similarly, for omega hat less than 0. And these are the only zero crossings in the interval minus pi to pi, it turns out. So you have 2/5 pi, it's about here. You have 4/5 pi, it's about here. So it's more like here. This is 2/5, 2 pi over 5. And this is 4 pi over 5. And then you have zero crossings over here to the left. Negative signs. And what does it look like in between? Well, it turns out to look something like this. That's pretty good for me, drawing. I know you guys are so much better at drawing stuff. But it looks like that. And just for completeness, what is its value at omega hat equals pi? Sine of 5/2 pi is equal to 1. So this value here is 1. All right, so there's what the Dirichlet thing looks like on omega hat running from minus pi to pi. Now, for general L, remember I said this reveals the structure for general L. For general L, this is what it looks like. It still has an L at omega hat equals 0. And as you go out, so for general L, we have dl of 0 equal to L, and zero crossings at integer multiples of 2 pi over L, pi over L. You know, things like that. So omega hat values where L omega hat over 2 is equal to integer multiple of pi, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. as far as you have to go out. And that's the same as 2 pi over L, 4 pi over L, 6 pi over L. So plus or minus 2 pi over L, plus or minus 6 pi over L, or for 4, etc. All the ones that are out, you know, that lie in the interval minus pi to pi, those are the ones we're worried about but those are the only ones we worry about because we're always graphing this thing on minus pi to pi. Okay? And the peaks there, because the denominator sine of omega hat over 2, what does that do on the interval minus pi to pi? Well, it increases to 1. It starts at 0 and increases to 1 as you go out to plus or minus pi in absolute value. So this goes to 1, increasing as omega goes from 0 to plus or minus pi. The heights of the peaks in the dl of omega hat get lower and lower and lower. And when I talk about peaks, I'm talking not about positive peaks, but the negative peaks as well. So as omega hat goes to plus or minus pi, that happens. And that should remind you of something. That should remind you of something we've already seen before in this class, briefly. Right? What does it remind you of? What does that picture kind of remind you of? A poop. Yes, a sinc function. It's kind of like a sinc function. It goes like, it looks sine-like, and its biggest peak is at 0, and the peaks tend to waffle down as you go out. And sure enough, some people call this thing a periodic sinc function for that reason. So in some quarters, some less sophisticated quarters who don't like to deal with French names like Dirichlet, people call this dl of omega hat a periodic sinc function because it looks like a sinc. And why periodic? Well, it turns out it is 2 pi periodic in omega hat. If you go out to the interval, say pi to 3 pi, it's going to climb back up to the peak of 5 at omega hat equals 2 pi, and then go down again, and so on. All right. So that's your dl of omega hat. Now, back to the problem at hand. Okay, so back to the problem at hand. So where we started with this, that was the following. The frequency response of the L-fold running summer running, why can't I spell this right? Maybe it's because there's 3 n's in there, and it just makes me feel like over-end when I get to the third one. Running summer is h hat of omega hat equals dl of omega hat times e to the minus j l minus 1 over 2 omega hat. Okay? So what is the magnitude of h hat of omega hat? It's just the absolute value of dl of omega hat. So you just take that picture, that's the case for L equals 5, and you take the absolute value of it. Question? Okay, that, again, whenever you have e to the j theta and theta is real, the magnitude of that is 1. Okay, so this is because magnitude of e to the minus j L minus 1 over 2 omega hat equals 1. So when I take the magnitude of the whole thing, all I get is the absolute value of the thing multiplying the e to the j theta term. Okay, this is one of those things. That's another thing. I'll write it over here on the side board where the people watching, this is the subliminal board. You can't see it. You can't see, you can see me, right? But you can't see this board. E to the j theta magnitude equals 1 when theta is real. Okay, that is now part of your subliminal video lecture. You know, this, you'll remember that tonight when you go to sleep. Or not, whatever. Okay, so anyway, that's the magnitude. What about the phase? What about the phase? As for the phase, we have a kind of a nominal phase, which is given by whatever's multiplying the j in this expression. So as for the phase, again, this is as for the case when we were dealing with the high-pass filter. As for the high-pass filter, we need to, that doesn't look right. As for phase, as for high-pass filter. So how about like with the high-pass filter? That sounds more casual. Sounds like 80s, you know, San Fernando Valley, whatever. Now, Robert, I hope you're watching this out there in greater LA, and I hope you're feeling safer than some of the people out there are feeling. But anyway, as for the phase, and there was someone else from greater LA, right? Katie, are you out there? Well, even if you're saying yes, I can't hear you. Sorry. I mean, anyway, as for the phase, like with the high-pass filter, we need to account for the sine of the d5 of omega hat. The sine of, in general, dl of omega hat, when it's negative, it contributes a pi. Okay, so what we do to graph the phase, this is what I like to do. You know, you may hate it, and I'm sure there are people who don't like to do it this way, but I like to do it this way. So first what we're going to do is graph the nominal phase, which is this. It's L minus 1 over 2 omega hat with a minus sign in front of it. This 2 looks like an L, doesn't it? Can you even see? All right. So for L equals 5, that's the case we're looking at. This is, what is 5 minus 1 over 2? Minus 2 omega hat. All right, so let's graph that versus omega hat. So here's pi, here's minus pi. Is that good? Kinda. Here's 2 pi. So it's going to be minus 2 omega hat. So this is going to be minus 2 pi, and this is going to be 2 pi. All right, so that's the graph of the nominal phase for L equals 5. Now, where is d5 of omega hat negative? It's negative between 2/5 pi and 4/5 pi. So here's 2/5 pi, and this is 4/5 pi. And it's also negative out there on the left. Same kind of values. So to get the actual phase of this dude, we have to add a pi, or subtract a pi as appropriate, on the intervals on which dl of omega hat is negative. So let's first do this one, and let's add a pi to this picture on that interval. So I'll write this here because I'm going to switch boards. You add a pi on this interval, and I'm going to subtract a pi on this interval. And that'll leave me with something. And I'm going to have to make a final adjustment. As you see at the end, to get everything between minus pi and pi. So first step of this process is I have minus 2 omega hat going out to 2/5 pi and minus 2/5 pi. So that's like this. And at this point, this is minus 2 omega hat, so this is minus 4/5 pi here. Minus 4/5 pi, I have to add a pi to that. What does that give me? It gives me 1/5 pi. So put this on the bottom. So this is 1/5 pi here, pi over 5, and that's still going to have the same slope. Here's pi, here's 4/5 pi. It's going to go like that. And over here, remember the phase has to be an odd function. You're going to have the reverse of this. So here's minus pi, minus pi, minus 4/5 pi is here. So let's call this 4 pi over 5, minus 4 pi over 5. You're going to have same thing like so. So this is minus pi over 5. And what about between 4/5 pi and pi, and between minus 4/5 pi and minus pi? You have to add 2 pi to the phase to get it in the interval minus pi to pi. So I take minus 2 pi and I add 2 pi to it, I get something that looks like this. And the same thing over here. Subtract 2 pi from the top, you get this. They're all slope minus 2. And how high does this one go? I always forget. I have to figure it out. But anyway, this is what it looks like. And let me explain where I got these things. This comes from add 2 pi to minus 2 omega hat on the interval 4/5 pi less than or equal omega hat less than or equal to pi. And you subtract 2 pi from minus 2 omega hat on the interval minus pi less than or equal omega hat less than or equal to minus 4 pi over 5. Okay, and these are to get phase into minus pi to pi. All right, so that's what the phase looks like. And for general L, it's going to be more complicated. You're going to have more of these linear branches. All of these things have slope minus 2. All of these so-called branches have slope minus 2. Okay. All right, so those are crucial examples. Okay, we did a high-pass filter, we did a low-pass filter, and we did this L-fold running summer. Crucial examples, they come time and time again, things like this. And lots of more complicated things get built in the same way out of these as pieces. All of these examples, all these crucial examples, have something in common, aside from their cruciality. Okay? So all these crucial examples have something in common. That their h hat of omega takes the form h hat of omega hat is equal to some real valued function I'll call a of omega hat times e to the minus j alpha omega hat plus beta for some real valued function a of omega hat, and real numbers alpha and beta. And this form of frequency response, there's a name for a system that has a frequency response of that form. Many other systems have such frequency responses. So terminology, a system whose frequency response takes this general form is called a generalized linear phase system, a GLP system, if you will. And it turns out there's a whole theory of these. And so next time what we're going to do is we're going to pick up on that a little bit. We're going to talk about, well, I don't know how deep I'm going to get into this for now, but anyway, I just want to leave you with that thought, that there's a name for systems like this. The examples we've considered are special cases of a much more general thing called a generalized linear phase system. Why is it called that? Well, look at the phase. It's linear in omega hat, or at least affine. Okay, get to that next time. Hope you're doing okay. I really miss you guys. And I'll see you soon. Takes a while to stop the video. That awkward moment when you're trying to stop the video. I have to wipe down the mouse too before I leave.